Welcome to the DIY Honda Garage channel. The Diagnostic Trouble Code, DTC P16E3, indicates a PGM-FI-Battery sensor LIN, local interconnect network, communication error, in Honda CRV models from 2017 to 2022. This code signifies a problem in communication between the battery sensor and the Powertrain Control Module, PCM, affecting the vehicle's performance. The 12-volt battery sensor is crucial for monitoring battery voltage and sending this information to the PCM. The sensor is typically located near the battery, connected to the negative terminal with a wiring harness. Without proper communication, the vehicle may exhibit issues related to power management and battery diagnostics. Thus, addressing this DTC is important for vehicle functionality and reliability. The battery sensor in a Honda CRV plays a pivotal role in monitoring the charge state and performance of the vehicle's battery. It communicates vital information concerning voltage and battery conditions directly to the Powertrain Control Module, PCM. This communication occurs via a local interconnect network, LIN, which is a low-speed protocol used for sensor data transmissions in vehicles. The battery sensor is located in close proximity to the 12-volt battery, connected at the negative terminal. As such, if any disconnection or short occurs in this line, the PCM fails to receive critical data, subsequently triggering Diagnostic Trouble Code P16E3. To ensure vehicular reliability, it is essential that the battery sensor communicates effectively. Several factors may lead to the occurrence of DTC P16E3. Firstly, loose terminals on the 12-volt battery sensor, especially at the negative terminal, could disrupt communication between the sensor and the PCM. Secondly, a faulty local interconnect network, LIN, communication line can also cause this error, indicating that the wiring or connection may be compromised. Between the battery sensor and the PCM, if there are any short circuits or open wiring segments, it will result in impaired functionality. Each of these causes must be inspected meticulously during the diagnostic journey to restore proper communication and vehicle performance. Symptoms associated with DTC P16E3 primarily revolve around battery-related functionality and PCM diagnostics. A significant symptom is the loss of communication between the battery sensor and the PCM, which can lead to inaccurate readings regarding battery performance. This issue may cause the vehicle to experience battery performance issues, potentially impacting engine starting ability or power availability during operation. Furthermore, drivers may notice warning indicators on the dashboard related to battery charge or electrical systems. These symptoms collectively signal that attention is required to address the LIN communication error between the battery sensor and the PCM. In the first troubleshooting step for DTC P16E3, the goal is to confirm the presence of the code by leveraging the Honda Diagnostic System, HDS. Begin by turning the vehicle to the on mode with the ignition. Then use the HDS to clear any existing DTCs, including P16E3. After clearing, switch the vehicle to off mode and wait for approximately 60 seconds. Finally, turn the vehicle back to on mode and using HDS, check if DTC P16E3 is still indicated as either a pending or confirmed error. This initial step is crucial as it helps differentiate between a consistent error and a transient issue, establishing a baseline for further diagnostics. In the second step of troubleshooting for DTC P16E3, it is essential to conduct a thorough check for additional Diagnostic Trouble Codes, DTCs, using the HDS. Specifically, you should look for related codes like P16E2, which indicates an ACG LIN communication error, and P16E8, which corresponds to a shutter grill LIN error. If either of these codes appears, follow the designated paths provided in the troubleshooting protocol. Detecting related DTCs can provide insight into potential underlying issues affecting the battery sensor's communication, and addressing them may resolve the root cause of the P16E3 DTC. This troubleshooting step requires checking once more for Diagnostic Trouble Codes, DTCs, using the Honda Diagnostic System, HDS. The specific focus is to determine if DTC P16E3 is present, which represents a shutter grille LIN communication error. As with previous steps, if this code is confirmed, directional steps will guide you to further analyze and rectify potential wiring or component issues related to the shutter grille. If P16E3 isn't indicated, proceed to Step 12 to continue the systematic troubleshooting approach for DTC P16E3. This proactive step avoids overlooking additional communication errors within the vehicle's electronic system. Step 4 involves determining possible failure areas within the LIN communication system, specifically between the battery sensor and body ground. Start by ensuring that the vehicle is turned to the off or lock mode. Disconnect the 12-volt battery sensor 2P connector, and then check continuity between test points as designated in the diagnostic protocol. The first test point is the female terminal, number 2, of the battery sensor connector, and the second is the body ground. If continuity is confirmed, advance to the next troubleshooting step. However, if no continuity is present, this suggests an issue that requires further investigation. Moving to the fifth troubleshooting step, you should first jump the SCS line using the HDS and wait for more than 1 minute. This setup allows you to examine continuity between the battery sensor 2P connector terminal number 2 and body ground. It's important to check this while progressively disconnecting multiple connectors, including the alternator 1P connector, PCM connector B, 51P, and the shutter grille connectors. Disengaging each connector one at a time aids in identifying where continuity is lost. If disconnecting any connector results in losing continuity, it indicates that the LIN communication line is functioning correctly, and you will need to replace the faulty component causing the open communication line. In Step 6, the focus shifts back to the battery sensor. Begin by reconnecting the 12-volt battery sensor 2P connector. Next, disconnect the alternator 1P connector and proceed to measure continuity. Make sure your test conditions are set correctly with the vehicle in off mode. You're examining the continuity between terminal 1 of the alternator 1P connector and body ground. If you find continuity here, it's likely that the 12-volt battery sensor is faulty and should be replaced. If continuity is absent, you will then follow up with the next steps to investigate further, as an open circuit may indicate an underlying issue with the wiring. Step 7 also kicks off with jumping the SCS line with HDS and allowing a minute for the process to stabilize. Follow this by disconnecting critical connectors, including the 12-volt battery sensor 2P and PCM connector B, 51P. At this point, you will again check for continuity between the sensor and the PCM. If you find that continuity remains, this indicates a functional LIN, local interconnect network, wiring system. In such a case, look for any authorized service bulletins regarding DTCs and associated symptoms, or consider replacing the PCM if troubleshooting data supports doing so. However, if continuity is not found, this would suggest an open wire in the LIN that needs repair. As you progress to Step 8, first disconnect the 12-volt battery sensor 2P connector. Next, ensure the engine is off and examine continuity between the terminal intended for the battery sensor and a body ground point. If continuity is confirmed, you are on the right path, allowing you to proceed with further testing steps. If no continuity presents itself, This might indicate a short in the LIN communication line between the battery sensor, the alternator, and the PCM. You'll need to perform wire repairs to rectify the situation and restore proper communication. In continuing the troubleshooting process to step 9, once again, jump the SCS line with HDS and wait for over a minute. Subsequently, continue checking the continuity to the body ground through the relevant sensor wires. During this examination, disconnect each of the connectors specified, including the PGM-FI-Battery, alternator 1P, and upper and lower shutter grille connectors. If, upon disconnection, the continuity disappears, it signifies that the LIN communication is functioning well. This implies that the issue likely resides within the components causing the open line when disconnected. Thus, replacement is required. Step 10 follows up with reconnecting the previously disconnected 12-volt battery sensor 2P connector. Following this, the next task involves disconnecting the shutter grille, both upper and lower, 4P connector. With the vehicle in off mode, assess continuity between the third female terminal at the shutter grille connector and the body ground. If continuity is present, replace the 12-volt battery sensor as it is confirmed faulty. If continuity does not exist, proceed to the next diagnostic steps to uncover further potential issues, revoking proper connection and communication. As part of Step 11, you will again jump the SCS line with the HDS, letting it sit for over a minute to stabilize communications. After this setup, proceed to disconnect the 12-volt battery sensor 2P connector alongside the PCM connector B51P. The focal point of this check is to measure continuity between terminal number 2 of the battery sensor and terminal number 40 of the PCM connector. Establishing continuity will indicate that the wiring is intact, leading to further troubleshooting in case of issues. However, no continuity suggests that repairs are needed in the LIN between the module and the battery sensor. In this step, begin by ensuring that the vehicle is off, as you will need to check for blown fuses. Locate fuse number A24, which is a 10-amp fuse situated within the underhood fuse/relay box. Once you find it, inspect whether the fuse is intact or blown. If the fuse is not operational, it indicates a critical failure in the circuit. In such a case, repair the short within the +B horn wire, which connects from the 12-volt battery sensor to this fuse, and proceed to replace the blown fuse as well. Electrical integrity is crucial for the PCM to receive necessary data for operational efficiency. Step 13 requires that you disconnect the 12-volt battery sensor 2P connector to begin measuring voltage. You will measure the voltage between terminal number 1 of the connector and body ground with the vehicle still in off mode. Assessing whether the voltage corresponds to battery voltage will provide insights into whether there is a break in the +B horn line. If battery voltage is detected, it suggests functionality in that line, and you can progress to the next steps. If not, this indicates an open circuit, necessitating repairs to the wire between the sensor and the A24 fuse. In the final step, reconnect all relevant connectors following the measurements from the previous steps. As in previous troubleshooting steps, you will perform a jump of the SCS line with the HDS for a minute. Disconnect the PCM connector B51P, focusing on checking continuity once more between the 12-volt battery sensor and the PCM. If continuity exists, congratulations! The LIN wiring is intact and may indicate the necessity of replacing the 12-volt battery sensor if no error is resolved. On the other hand, finding no continuity will highlight an open circuit along the communication line between the battery sensor and the PCM, necessitating appropriate wiring repairs. Following the troubleshooting process, the final verification step is critical to ensuring all repairs have rectified the original issue. Begin by clearing any remaining DTCs using the HDS. After clearing, recheck the system for DTCs to confirm that none remain active, particularly DTC P16E3. Once confirmed, proceed to perform a functional test on the battery sensor to ensure it operates as intended within the communication ecosystem of the vehicle. Ensuring reliable communication between the battery sensor and PCM is essential for vehicle performance. If all functions are normal and no codes are present, then the repairs can be considered successful. Preventive maintenance can play an important role in avoiding future occurrences of DTC P16E3. Regularly inspecting battery connections and ensuring they remain secure can help mitigate issues relating to loose terminals that could interfere with LIN communication. Additionally, checking for signs of corrosion or wear on the connectors and wiring will safeguard against degradation over time. It is also imperative to ensure vehicle software and diagnostics are kept up to date, as updates may contain crucial improvements to vehicle communication protocols. Consistent preventive measures can significantly enhance reliability and performance. In summary, the systematic approach in diagnosing DTC P16E3 revolves around identifying and remedying communication issues within the battery sensor and PCM interactions. Understanding the role of each component in this system aids in accurate diagnostics and effective troubleshooting. Essential steps include checking the integrity of connections and inspecting wiring to ensure no opens or shorts exist that could impair communication. Regular inspections and preventive maintenance also contribute significantly to reducing the risk of recurrence of such DTCs. By adhering to these processes, automotive professionals can enhance vehicle reliability, ensuring that owners are satisfied with consistent performance. Please like and subscribe to the channel. See you next time.